This is a demonstration of the Naue PavedRoad AASHTO calculator. To get started, select the calculator in the list of apps within the design suite of the Naue portal and press the calculator button. We can choose between imperial units and metric units. We'll select metric units in our example. First, we define the traffic data. Traffic volume to be expressed over the design life of the road is given as so-called equivalent number of 8-ton axle loads, ESLs. In our example, we will define a collector road with 200,000 ESLs. The reliability index represents the confidence level that the pavement will meet or exceed its design performance. For our collector road, we'll define a value of 80%. The combined standard error accounts for the differences between the actual and predicted pavement performance. A value of 0.45 is used. The initial serviceability index represents the pavement's smoothness and ride quality at the time of construction. We'll use a value of 4.2, and the terminal serviceability index defines the lowest acceptable pavement condition before major rehabilitation is needed. A value of 2.0 is chosen. Now we are defining the layout and material properties of the pavement. The asphalt wearing course has a thickness of 7.5 centimeters. The layer coefficient is a dimensionless value that reflects the material properties and performance characteristics of each layer. We'll use a value of 0.44 for the asphalt wearing course. The base course has a thickness of 20 centimeter and a layer coefficient of 0.14. The drainage coefficient represents how well water is drained from the pavement structure. It is expressed as a dimensionless number as well. We'll use a value of 1.0. The material type to be defined for the quality of the base course material is now selected. In our case, we'll select a crushed stone. Underneath the base course, we'll define a sub-base course with a thickness of 30 centimeter, a layer coefficient of 0.11, and a drainage coefficient of 1. The material type is also a crushed stone. Finally, we are defining the subgrade, which can be expressed as a CBR value or a resilient modulus. In our case, we'll define a CBR value of 1.5. Now the last selection we have to make is the optimization strategy. The first one is a cost optimization, which means we are potentially reducing the thickness of the unbound layers. And the second option is an optimization of the road service life, which would be a traffic benefit ratio. We'll go for the first option to potentially reduce the thickness of unbound layers. The next page shows a direct comparison between the optimized reinforced solution on the left side and the originally defined unreinforced pavement section on the right side. The calculation results show that the unreinforced solution meets the required structural number of 3.7 with a given pavement cross-section and material properties. The geogrid reinforced section allows roughly 18 centimeter of aggregate saving over the unreinforced section by using one layer of CombiGrid 3030 Q1 below the subbase course. We can further optimize the proposed reinforced solution and create a customized solution by clicking Yes and continue the calculation process. First, we will eliminate the decimal places in the calculated layer thicknesses that arise from rounding. Subbase course will be defined with 15 centimeter and the base course is slightly increased to 17 centimeter. We can further optimize the section by selecting a stronger CombiGrid type at the base of the subbase course. Therefore, we delete CombiGrid 3030 Q1 and select the stronger CombiGrid 6060 Q1. The structural number has now increased to 3.97. This allows us to further reduce the base thickness to 15 centimeters. Now we can optimize the asphalt wearing course. Based on the AASHTO guideline for flexible pavement design, a minimum thickness of 2.5 inch, which is approximately 6.5 centimeter, is required for pavements with 150,000 to 500,000 ESLs. Reducing the asphalt wearing course to 6.5 brings the calculated structural number below the minimum required value of 3.7. If we now increase the base course to 16 centimeter, we bring the structural number up again above the minimum required structural number to a value of 3.71. By clicking on the Continue button, we'll get an overview about our calculated customized reinforced layout. Clicking on the next Continue button allows us to print a PDF report of our calculation. This report is now saved in the download folder on your hard drive. The design report is summarizing the defined object parameters in terms of traffic data, the layout and material properties for the asphalt wearing cores, the base cores and sub-base cores, and the strength of the subgrade. It shows the chosen optimization strategy and the solution of the customized reinforced solution on the left side and the originally proposed unreinforced solution. We can see the reduction in thickness of the base cores, 16 centimeter versus 20 centimeter, and the sub-base cores has been reduced to 15 centimeter versus 30 centimeter in the unreinforced case by using one layer of CombiGrid 6060Q1. Also, the asphalt wearing cores could be reduced by 1 centimeter. On the last page, we can see a summary of the thicknesses and also the structural number calculation.